Okay, people are coming in out of the waiting room. I have to get rid of that waiting room. I thought I already did that already. I'm not sure if everybody has entered. Okay. I thought I got rid of that waiting room. I have to remember to get rid of it. It's not really helpful. Okay, I think everybody's in.
Did did that link I sent you help at all, Professor Kraft?
That
Did it
wasn't
give
about the waiting room. That was something else.
Okay.
Yeah, that I didn't have. Yeah, I checked. I didn't have that turned on. Yeah, I forget. There is a way to. I turned it off in my other classes, and I thought I turned it off on this one. And I probably just forgot to. But yeah, I found out how to turn off the waiting rooms because it's. I don't think it's really needed. We don't seem to be one of the. We're not. It doesn't seem like we're the kind of school that gets attacked by too many trolls and people like that.
Right.
Okay, so I think everybody. Let's see. Admit. I have to admit some more people. Okay. All right. Yeah. Um. Yeah. I wish I could turn off. I don't know if I can turn off the waiting. I can turn off the waiting room for the class after it's over. I'm not sure if I can turn it off right now while the class is going on. Okay. All right. Most people are here now. If do you see people waiting in the waiting room from your like? Can you let me know if somebody's waiting in the waiting room?
Sure.
Can you guys see it?
Um, I guess maybe only if you're sharing your screen.
Oh, okay. Yeah. Oh, one person's waiting, so there's somebody else. Okay. All right. Yeah, I have to keep paying attention to see if there's anybody waiting in the wait. Yeah, I got to turn that off. That's just not a very good idea. Because if somebody comes late, I probably won't notice them. Okay. Um, so let me go ahead and switch to screen sharing. Okay. I'm kind of setting things up. And I want to. Let me set things up real quick. All right. Oh, here's what we're going to talk about today. We're well, there's a reading assignment for Thursday. We're going to start talking about the input data structure. Today we'll finish talking about the frame buffer, the output of the render. And on Thursday, we'll start talking about the input to the render, which is the scene, what's called the scene package. And there's a reading that I think is kind of helpful. It's another online book about rendering. It's about, actually, the book's about OpenGL and what's called ray tracing, but it's got a nice introduction. So it's got this kind of medium long page. That's like a nice overview. So it's a good reference to read. Okay. So read that reference for Thursday. And we're going to start talking about on Thursday the scene package in the renderer. Okay. What I want to do today is go back to these pixel examples and just go through more examples of code. Last week we talked more about the idea of pixels. We were zooming in on the screen and looking at pixels. Now we actually want to start looking at actual code. Okay, and actually before that, let me download the homework assignment. Okay, let me show you something real quick in the homework assignment. And then if anybody has any question, we can also ask, look, if anybody's got a question, we can go over that now. Okay, so, you're supposed to create this output image using this as your part of it. This is part of the input image. Okay, so you have to read in this image and then manipulate it into a viewport. Okay, now one thing I did in this, this is the outline program that I gave to you. I already read in this image here, but I do it using a command line argument. And do it this way. Make sure your code that you send in uses this. And here's why. Okay, your program has to read a file. Okay, where is the file your program reads? I don't want you, when I grade all your homeworks, I'm going to put the file in a certain place, and I want everybody to read the same file. I don't want to have 50 copies of this file on my hard drive. Okay, so the easiest way for me to make sure that everybody can read my copy of this file is to have it passed as a command line argument. So this is a way of abstracting in computer science. Instead of having you hard code into your code the location of this file, and then I have 47 people all have this file in a different folder, it's better that you actually get it off of a command line argument. Then I can compile everyone's programs and run them and have everyone's programs pointing at my one copy of this file. Okay, so it's an abstraction that makes running multiple pieces of code easier. That's what the command line is there for. So actually what I did here is that the program checks that there's a command line argument, and then the command line argument will be the name of the file to open. Okay, and then then it uses that command line argument here. Okay. Now, if I just compile this program and I run it, it gives an error. This is what we call a usage message. Okay, usage messages are typical of command line programs. When you don't run them properly, they tell you, this is how you're supposed to run me. You're supposed to say Java homework 1, name of a PPM file. Okay, so you should run this program with a PPM file on the command line. Okay, now I can do that here. The name of the PPM file is rebeltrooper.ppm. So if I get that name, I'm using TextPad, but when I run my program in TextPad, notice it prompts me for command line arguments. I set up TextPad so this program prompts me. Whatever IDE you're using, you could do it however way you want. So then I'm feeding it the command line argument. Okay, and my program doesn't run properly because I haven't written any code for it in here. So it doesn't see. I'm zeroing out the null that frame buffer, but the program ran this time. Okay, and if you want to run it from a command line, you can actually go here and open a command line, and then you would Java homework 1. Okay, if you run it this way, oh, I'm sorry, I misspelled that. Okay, see, there's the usage message. The usage message is saying you should have a command line argument. So I can go over here and give it a command line argument. I can use command line completion. Notice I just typed capital R. I just typed capital R and I hit the tab key and let the operating system find the file for me. And then, okay, now the program ran, it used the command line argument, but the program crashes because it hasn't been written yet. So please, use that part of code there, use that. Okay, so now what's nice about that is now you have this picture in a little frame buffer. I called it frame buffer embedded because you're going to take the data in this frame buffer and stick it into your bigger frame buffer. This is the frame buffer that you're building. So this is the frame buffer that you'll build that has size, see, 1000 by 600. So here you'll instantiate the big frame buffer, and you should read the pixels out of this embedded frame buffer into this big frame buffer. So you don't need to actually write the code that reads pixels out of this file here. You can use the library See, the library already knows how to read this file here. So here, I've read that file into a frame buffer, use that as a holding place for the pixels that you can then copy from here into this frame buffer. That makes things easier. You write less code, you use more library code, and use the library. That's the old saying. Use the library. Try to use the library as much as possible. Since the library knows how to read a PPM file already, let it do the reading. Okay. So I did this so that everybody would have. The main reason I put this in there for you is because I want to make sure that everybody read from used the command line argument to read this file here, so that otherwise I'd have to go in and start either changing people's code because if you hard code the name of this file and the location of this file into your program, then it's hard for me to run your program on my computer. So this is the way to have it not hard coded into your program. Your program will get a command line argument, and when I go to compile and run everybody's programs, I'll pass it a command line argument to one copy of this file that I have on my computer. Okay, so that's one thing I wanted to point out. Make sure you're using this. Now, if you don't like constantly having to type a command line argument while you're debugging your program, you can do the following. You can get rid of the command line argument and just here put the name of the file. Okay. Now your program doesn't need the command line argument. For debugging purposes, you can just compile and run this thing. Now it hard codes reading the file name. Okay, but don't turn it in that way. This might be more convenient for you while you're debugging, so you don't have to keep remembering to pass a command line argument, but don't leave it like this. After you've got your program debugged and working, go back to this. Turn it in, reading from the command line argument. But it's okay while you're debugging to do it this way, because it's a little bit more convenient. So you don't have, unless you just remember to keep giving it the command line argument. Okay? All right. So now other questions? Anybody, this is the demo code. This is the starting point for your homework assignment. Does anybody have a question about the homework assignment? Does anything come up? Is there anybody can run into any problems with the programming assignment?
I have a question.
Uh-huh.
So just looking at the picture that you want us to replicate, are you kind of expecting us to use the zoom tool to figure out the location of the pixels, or should there be some type of documentation?
No, no, use the zooming tools. Yes, that's a real good point. Use the zooming to, like, see our IRFRAM view. For example, where's the upper left-hand corner of this gray frame buffer? 725.25. Okay, see? So see, remember, you click on it, and IRFRAM view tells you where it is. How big is it? Well, click in the upper left-hand corner and find out where it is, and click in the lower right-hand corner, find out where that is, and then you can subtract numbers and find out how many pixels across it is and how many pixels down it is. Same way, this frame buffer that's in this viewport within this viewport is at that location. Okay. And notice that I clicked on it, it says 748. I didn't use funny numbers like 748. It's actually at 750. I pretty much used round numbers, but it's very hard to pick. You don't always get the exact right thing, but usually things will be round. Like there, it's 750. It's at pixel 750 horizontally at pixel 50 down. That's where this upper corner is. Okay, so like this corner here, it's at 580, 420. Yeah. Now, okay, so now that's getting the location. And then if you want the color, IRFRAM view will do it for you too. Like, what's the color of this red? It's 192, 56, 14. What's the color of this dot? It's 180, 100, 255. Yeah, so that's a good question. Yeah, use the tools. So I did not document the exact location of everything in here because you can get them. Usually you can just use IRFRAM view. IRFRAM view can give you, or you can use one of the zooming tools to figure out where everything is. Same with, like, you have to find the width of these stripes. you have to find the lengths of these stripes. You know, you do that, you know, click, 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 or zoom. Like, you know, you could either zoom or click, yeah, and find out how wide one of those stripes is. What's the color of the stripe? How wide is it? How long is it? Okay, right? So use tools in the, either use EarthRAM View can do a lot of this for you. So use EarthRAM View as much as possible, and then any other tools that we have that are in the Pixel Utilities folder to get as much information as you can.
So
We
if
are,
we're just like a few pixels off, that's not a big issue.
Oh, I won't even notice. Yeah. Now I used round numbers for every.
Okay.
Pardon me?
Okay, yeah, thank you.
Yeah, I won't. Yeah, of course, I'm not going to notice if you're 3 pixels off in this corner. But I also used round numbers for most of the numbers. So things aren't at 76, 126. It'd be 75, 125. Yeah. So I didn't use any really off-the-wall numbers in here. But yeah, certainly if you're off by 1 or 2 pixels, I probably won't notice. I do. One way I can test your program is to do what we call A/Bing it. Like here's I can't. Let's see. Yeah, I can oh, here. If I wanted to really test if your program is perfect or not, I would just open like, I'd open 2 image files. What am I doing? Did I make a copy of the wrong thing? Oh. Okay. And you know, I can put them on top of each other. Well, actually, now I have too many things open. I do this all the time when I'm debugging my own code. Open 2 images and just switch between them. You'll find out real fast if you're even off by 1 pixel. This trick will show you. See how I can go back and forth between them? If one of them was off by even a pixel, you'd see a tiny little movement in the picture. Okay. Notice EarthRAM View is real nice. If you open one file and open the other, they're right on top of each other. Okay. And then if you switch between them, you'll find out real fast if you're even off by 1 pixel. If you're off by color, EarthRAM View is a great program. EarthRAM View always does things in a really nice way. So if you open a file, if you open 2 copies of a file, EarthRAM View will open them right on top of each other, and you can just go like this and A/B them. Test, look at one, look at the other, look at one, look at the other. Okay.
I think it'd be easier if you
Pardon?
just use. I think it'd be easier if you use an SHA-1 hash on both of those files.
But then you won't know where the differences are. Yeah, you could hash the files. That'll tell you whether they're the same or not, but it won't tell you where they're different. Your eye is really good at picking up differences. If you do this, you'll find out differences you'll see differences pretty quick if you do it this way. Yeah, you could hash the files too. Yeah. Yeah. So yeah, you can't, when you're working with pictures, it is a little bit tricky to compare pictures because with text files you can diff them. There's programs that'll tell you the differences between them. There are visual, if you know what a diffing program is, there are visual diffing programs, but I can't find a free one. The only visual diffing programs I know are you have to pay for them. So this is my visual diffing, is open the 2 files up on top of each other and just switch between them. Okay. Okay. So, but I'm not going to probably notice if you're off, but I probably won't do this to check everybody's file. I do this when people ask me questions. If somebody has a question about their file and I want to see if they've done everything perfect, I might check it this way. But when I'm grading everybody's, I'm going to pretty much do things in a much more automated way. But this is good for you. This is a nice way to, your eye is pretty accurate. If you do this and you're off by just a tiny amount, your eye will probably catch it. You'll probably see how one is different than the other. You'll see some little switch between them. Okay. All right. So what about other questions about the homework? Any other questions so far about the homework assignment? Okay. Anybody else have any other questions? Oh, here's an outline of the steps that would, this gives you a little bit of, give you some hint about what order to do. I think if you do them in that order, it tends to be a little bit easier. Okay. All right. So let's go to the folder. Well, let's see. I want the Pixel Utilities folder and the Pixel Examples folder. Okay. I want to look at this code that's in here. Just look at some interesting examples of programs. Okay. There's several things. The files in here show you a couple different things. For example, notice that here's the Yoda. Here's a picture of Yoda, a Lego Yoda. Here's another picture of Yoda, a Lego Yoda. And then here's another one. Where's the picture? Microsoft's become really a bad company in a certain thing. Let me show you something real quick. I like to use Irfan View. Okay, if you go here to Irfan View, you can go to Options, File Associations. You can tell Irfan View to make Irfan View the owner of all image files. Irfan View is a very good image file viewer. So go ahead and let it be the owner of all the image files. Okay, and then you click OK. Let's see if this happens. Notice it didn't work. Windows won't let programs take the file association of GIF files and JPEG files and PNG files. This is new in Windows 10. So see, if I go back over here, file associations, notice I've chosen PNG. Where is it? Oh no, I turned it off. Oh, put it back. Okay, PNG, JPEG, okay, GIF. See, those are the ones. No, okay, I had them picked before. So notice that I turned on GIF, I turned on PNG. I also want RAW, and then I click OK. Nothing happens over here. See, PNG is still owned by Photo Viewer. Okay, and if I go back over here, see, Irfan View did not get ownership of PNG. Now, sometimes I actually get a pop-up message from Windows saying a program tried to take over PNG files, but we fixed it for you. Windows 10, I have not been able to figure out how to do this. Windows 10 is adamant about the Photo Viewer, which is owned by Microsoft, owning PNG files. Okay, it seems to, now Windows 7 didn't act this way, Windows 8 didn't act this way. This seems to be something new in Windows 10. It makes it, so far I haven't figured out how to fight with it. It makes it so you cannot change the association of this file to Irfan View. Now Irfan View knows how to open them. Oops. Irfan View certainly can open them, and it's a lot better at it than Irfan View is way better at all of this than Microsoft's Photo Viewer, which is not a particularly great program. Okay, but all these should be Irfan View icons, and Windows 10 for some reason has become really stubborn about this. If any of you figure out how to change it, you can go through and use all the tools you have for changing file associations. I can't get it to work with PNG files. Every time I change the file association of a PNG file, Windows ends up changing it back to Photo Viewer. Yeah, every trick I've been able to try so far of changing, I want to change it to be associated to Earthran View, and Windows 10 always makes it go back to Photo Viewer. Be nice to know if there's a trick to get around that problem. Okay. All right. Now, what's the point of me having Yoda, 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 Yoda here? Okay. They're all different file formats. We talked the other day about this idea that you can store pixel data in lots of different ways. Okay. Okay. So there are lots of different files for storing pixel data on your hard drive. And over the years, tons of these have been invented. There's probably something like 100 different file formats. Actually, if I go back and open Earthran View again, notice how many file formats Earthran View knows about. And this is not all of them. This is not all of them. And this is, this is not even, there's way, way more than this out there. And people are inventing new file formats almost every day. Apple just recently invented one that they use on their iPhones. It's not in this list. And Google recently invented one that they're promoting, and it's starting to get used. It's weird. People are inventing new file formats for pictures left and right. So Apple recently invented one. Google recently invented one. Right now, the two most common are JPEG and PNG on the internet. Okay. So what do these things do differently? They store the pixels in different ways. Okay. And you notice all of these store the same picture, but they are different sizes. If you look down here, like this one's 192 kilobytes, this one's 29 kilobytes, this one's 9 kilobytes. Notice the difference in size. This one's way bigger, this one's smaller, this one's much smaller. Okay. This one's back to being big again. This one's also big. This one's kind of medium sized. This one's back to being big again. Okay. Okay.
So have some of them been compressed
Yes.
with loss? Or
Yeah,
loss?
they're all lossy compression. So this one is a compressed format, this one's a compressed format, and this one's compressed. So the ones that are small are compressed. GIF, JPEG, and PNG are compressed. Okay. Now, let me see. Let me. Okay. So here you can see the sizes of them. So this one is not compressed. This one's compressed. This one's compressed a lot. This one's not compressed. This one's not compressed. This one's not compressed. This one is, and this one's not compressed. Okay. All right. So there's a lot of redundancy in pictures. If you look here, there's all this white space out here. Do you really need to store all those pixels and just say that, what the compression algorithms will do is they'll say things like, there's 100 pixels in a row with the same color. So compression algorithms find redundancy in the picture, and then they just store the information about the redundancy. Okay, so that's so many of these are compressed. Now, what's interesting are these two. These two are not compressed. What that means is they actually are storing an array of pixel data. Okay, they actually store an array of pixel data. Now, this one, let me open it. This is actually a text file. Okay, that means it actually stores ASCII text. So when, this is saying that this is a PPM file of type P3. P3 means it's a PPM file that stores ASCII text. It's a picture that's 256 pixels by 256 pixels. So if I open this, Earthran View will look at, see, it's 256 pixels by 256 pixels. The pixel data is RGB, RGB, RGB. There's R, G, B, but as numbers in ASCII. That's actually, see what that R, it's not 1 byte, it's 3 bytes. It's actually 4 bytes because it needs a space there. So it's actually storing 4 ASCII characters, 255 space. Then for the G, it's storing 255 space. RG, 255, 2555, that's this white pixel in the upper left-hand corner. Notice that there's lots of white pixels. There doesn't get to be anything that's a little bit different than white till you start getting down here. So that's when you've gotten over to here and you've got start to get the top of his head. See, that's these pixels here. Okay. So this file format is it's very this is an old file format. It was used years ago when, for some reason, some people wanted an ASCII version of their pictures. Okay, so it's a standard file format that stores things as ASCII files, P3 ppm. Now let's look at this P6 ppm. Notice it looks the same. This is the P6 ppm. What's in here? This is the one that we're going to use most of the time in this class. Now, look at the difference. See, this one, the P3, is all ASCII. The P6 one starts out as ASCII text. This is what we call the metadata. It says, I'm a P6 file. I was created by IrfanView. I'm holding a 256 byte by 256 pixel by 256 pixel array. Each pixel has 255 colors to it. Then here's the pixel data. But the pixel data is now in binary. The pixel data is now not ASCII anymore. The pixel data is in this format of this one. It's an M by, well, it's actually this one. It's a one-dimensional array that's 256 by 256 with 3 bytes per pixel. Okay, so but you just see now. Notice this, and if I open this in in a text editor, I just see garbage. I can reopen this if I want. I'm going to reopen that pixel, that file. And I'm going to tell it to open it as a binary file. Now, TextPad can open files as binary files. Okay. So now I get a hex view of it. Notice that this hex view is going to agree with this, well, almost with this. See, this says 255. The hex view says FF. FF is the hexadecimal version of the number 255. These things were stored in decimal, not hexadecimal. They're text files with decimal number representation of every pixel data. There is another version that uses hex representation in ASCII. If you wanted your ASCII to be hex, then it would show FFFF here. It would be FF here, FF here. Okay? This is a good, getting your mind around this is a good exercise in starting to understand what we mean by everything being binary, but you can represent binary in ASCII or in hex or in decimal. Okay. This file format, which is the same as this one, they're the same thing. This file format is ASCII up to there. That's the ASCII part of it. That is this part here. Then it switches to being binary data. And then it switches here to being binary data. Here you can start seeing the top of his head. There's where some of the pixels turn to different colors. This junk over here is what this thing's showing. This is what it thinks is the ASCII character that this data represents. But these are actually non-ASCII characters. They're non-printable ASCII characters. Every once in a while, you get what looks like text. Notice that that's not really text. That just happens to be a string of bytes that fell in the range of ASCII data. So it looks like it's a string, but it's not really a string. It's just binary data that happens to fall in the range of ASCII. ASCII is the range from 0 to 127. The first 127 values of a byte are ASCII. From 128 to 255 are these funny characters that don't print very well. These are all numbers that are larger than 127. Okay, so you see ranges of what look like ASCII, but they're not really ASCII. And if you look at it here, you can, in this file, you see strings that look like they're character parts, but that's just a coincidence. They're just binary values that happen to fall in the ASCII range. Okay, so there's all kinds of ways of storing data on a hard drive. If you want to store an image file, you can store it all kinds of ways. This one is pixel data stored as ASCII. This one is pixel data stored as binary, but not compressed. These ones are not compressed. I'm sorry. These ones are not compressed. Then there are compressed versions. This one's a little bit interesting. This one says, well, let's look at this one. This one says raw. If you open it, it's missing the metadata at the beginning. See how this one has metadata at the beginning, then it starts the binary data. The raw one has no metadata. It only has the binary data. What makes it raw? Why do they call it raw? Does anybody see there's a little bit of a problem here? Why is the metadata even there?
It's the header for the file specification.
Yeah, but what is it? Why is it there? What is it? What needs to be specified? What's missing here? The same amount of all the data is here. This data here is the same as that data there. Why do I need this? It's an important question. It's a really good important question. What's kind of missing here? Why does this stuff, you know, all the relevant data, all the pixel data is right there. All the pixel data is right there. All the pixel data is right there. Why do I need this?
Is it explaining what it like compressed or something?
No, none of this, neither of these are compressed.
Oh, okay. Oops.
Let me give you a hint.
Is it so Earthfriend View could view it as an image?
Well, no, Earthfriend View does everything as an image. So it assumes that's all pixel data. RGB, 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 RGB. Okay. Let me give you a hint. Suppose I tell you I have 100 bytes of pixel data. Make it I should make it a multiple of 3. Suppose I tell you I have 99 bytes of pixel data.
Is it supposed to specify the dimensions of?
Yeah. Okay. Suppose I tell you. Suppose I have 99 bytes of pixel data. Now, 99 bytes of pixel data would be 31 pixels. But what do I need to know?
Dimensions.
Yeah. Where does a row start? When, how big? How many pixels per row are there? If I just give you 99 numbers, 99 bytes, you have no idea if it's a tall, thin picture or a wide, narrow picture. You have no idea.
So is that the width and the height and the RGB value then?
Here in the metadata.
Yeah, width, height, and then RGB below it or something?
Yeah, this is the metadata that says that this thing is that many pixels wide and this many pixels high. Then the program that reads this can count off pixels and know when it gets to the end of one row and goes to the next row, because it knows how many bytes are in a row, how many pixels are in a row. In this picture, in this here, Earthfriend View can open this, but has no idea. Notice that this is just pixel data. There's no flags in there that says you've got to the end of a row. Now, think about a text file. How does my text editor know that you got to the end of a line there?
New line character.
Which is a special character, which if you open this in the, now go back to opening this guy in the raw form. Open the ASCII version in binary. Okay. Here's that line, # space created by Earthfriend View. Then there's another line here. Go over here. There's the #. The # is the 1, 2, 3, 4th byte. 1, 2, 3. There's the #, pound space CREATED space BY space IRFAN VIEW. Now, W was the end of the line. How does the text editor know I got to the end of the line?
0A,
0A means
new line.
new line, which you can verify. Like we go over here. Look up an ASCII table.
10.
Where is it?
10. New line feed, right?
Right there. A, 0A, you know, what, it'd be 0A, new line. So 0A is new line. Okay. So a text editor knows when you've got to the end of a line, because embedded in your file are flags. There are flags that say new line. Okay. So for example, P6, here's P6, new line. Then we begin, now it shows up as a dot over here. Now on image files, there is no new line character. When a program like IrfanView is reading a pixel file, there's nothing to say, oh, you got to the end of a line, go back to the beginning. Nobody ever invented a new line character for pixel data. Text files come with their new line character, but image files don't. So image files have, in here, in this binary data down here is just the pixel data. There's no little flag saying, you've got to the end of a line, go back to the next line. Like there is with, see, this is a text file here. If you look at the binary version of this, you'll see that the end of every one of these lines is a new line character. So this is one row of pixels, but there's going to be a new line character there, and then there's going to be another row of pixels. So this is a text file, but it still doesn't know where the binary data ends. I mean, as a text file, it knows where the lines end, but it still has no idea where a row of pixel ends. It needs the metadata to know how many of these bytes form one row of the picture. Now, I don't know why no one ever came up with an end of line character for pictures, probably because it wouldn't be a very good idea. For text files, we have a notion of end of line. We have an end of line thing for text files. That's what it's built into the ASCII character set. In fact, there's actually two different ones. Some operating systems use CR, and some operating systems use NL. Okay. Let's see. Does anybody remember which one's which? I think Linux is the one that uses NL. I think Windows uses CR. And is it Mac that uses both of them? There's not even there isn't actually an agreement on what is the end of line character in ASCII. There's unfortunately more than one of them. Okay, so sometimes when you open text files, if I give you a Linux text file on a Windows machine, a lot of times Windows will open it improperly because it doesn't know where the end of line, it doesn't know. Linux uses a different end of line character than Windows does, so some Windows programs don't read Linux text files properly. Notepad is an example of that. Notepad doesn't read Linux files properly, and it doesn't read Mac files. Mac uses a different format for end of line. Image files don't have an end of row character. All right, now let's go back to the raw one. It's missing the metadata. So watch what IrfanView does. See, IrfanView, now Windows took over, so I'll drag and drop it. So I'm going to open this file with IrfanView. Now think about it. The metadata is missing. So IrfanView can see all this pixel data, but it has no metadata. What might IrfanView do? If you're a programmer and you've been handed a bunch of pixel data, and you don't know how many rows and columns there are, what would you do? What do you always do if you don't know something? Ask. If you don't know, you ask. What's this pop-up window? Remember, the metadata is missing from the file. So what's this pop-up window asking?
For the metadata.
For the metadata. 256 rows, 256 columns. Now let's look at what else was in that metadata.
It's 255 for the RGB, right?
Yeah, 250. Now that's this guy here, 8 bits per pixel. Okay. Well, actually, so see, we're not using 10 bits per pixel or 12. Actually,
Oh yeah, 24.
24. Yeah, it'd be this one here because that's 8 bits, 8 bits, 8 bits for 3 bytes. So that would be this one. Okay. So 256 rows, 256 columns. This one would be the thing that said how many values there are. Okay. Now, the other ones I'm going to leave in their default, and then I click OK. Okay, and EarthFriend View read it correctly. Now watch what happens if I do something funny. What if I give EarthFriend View wrong metadata? What if I say this is a 512 byte by 128? Are there 2 Yodas in that picture?
I see.
Think, go home, after class, think real hard about why there's 2 pictures of Yoda in there. Yeah.
They just ran through the same information to fill the space you gave it.
Well, okay. Think about what did it do. Here's the original Yoda picture.
Okay.
Can anybody tell me what's on the left? What's this guy? Where did this guy come from versus where this guy came from?
Do they look the same because the pixels are just so thin? It's actually 2 completely different Yodas going each made by 1 line off of the original picture.
Okay, yeah. So that's the right idea. All this data came from over here. Where did this Yoda come from, and where did this Yoda come from over here?
The one on the left is the odd numbered rows, while the one on the right is even numbered rows.
Exactly. Yeah. It's essentially going to be that when this was read, every other row was used to build this one, and every other row was used to build this one. Something like that. Okay. Okay. So I misread the pixel data. But when I misread the pixel data, I can get funny little things happening over here. Okay. Now let me do another misreading of the pixel data. Okay. Let me tell EarthFriend View the right dimensions. But let me tell it that the colors aren't in the order RGB. The colors are actually in the order BGR. There are some people who do that. Instead of storing RGB, they store BGR. Okay? That's what you get if you shift the colors around. Okay? Green's still green. Oh, green's still green. So actually what I did is I shifted the red and the blue. The reds and the blues are shifted over. So
I like that
now,
outfit better.
pardon me?
I was just saying I like that outfit better.
Yeah, it's not bad. Look, that turns out to be not so bad. Now let's try another one. Now every time you open EarthFriend View in raw mode, it remembers the last time you set things. So it always pops up in raw mode, whatever was the last choices you made. Okay. Notice that I went from RGB to BGR, so the G stayed in place. So the G's were right, but the R's and the A's were mixed up. This one will switch all 3 colors. No, I thought did I not read? No, again, that one still has the G in the middle. Oh, they all have G in the middle. None of these 3 shift the G. R, G, B, B. I wonder why that is. I never noticed that. Everyone seems to think the G belongs in the middle. Why they switch the R and the B and not the G, I don't know. Okay, so this is the usual one. Okay, now here's another thing you could do. Suppose you have RGB pixels, but instead of doing R, then G, then B, you could put all the R's first, then all the G's second, then all the B's. So that's allowed. Some people do it that way. They essentially go through all the pixels of the picture and pull all the R's out and put them first, then put all the G's and then put all the B's. Notice when I do that, I get a pretty messed up picture. Okay, so this one screws things up and it doesn't look like Yoda anymore. Okay, now I stored Yoda that way. See this, when you store pictures in all R's, all G's, all B, that's sometimes referred to as planar, because you store the R plane, then the G plane, then the B plane. So this image was actually 250. Now this one should be okay. See? Now what if I read, this one was stored in planar form. What if I open the one in planar form, but treat it as interleaved, where it goes RGB, RGB, RGB? This is a weird little picture. Yeah. Trying to tease out why that's 9 little Yodas. Yeah. Again, the EarthRAM view read the data is actually in planar format. So the data is actually holding all the red pixels first, then all the green pixels and all the blue pixels. But EarthRAM view is reading it as if it's going RGB, RGB, RGB. So you end up with 9 little, you have to think hard about why that turns out into 9 little Yodas. Okay. All right. So metadata is important. The raw image is the only one that the people traditionally call image formats without metadata raw. They're not very useful, because if I give you a raw image, somehow I still have to pass to you the metadata. Here, I know the metadata because these raw images are just these Yodas here. But if somebody sends you a raw picture over the email, you can just do trial and error to try to figure out what kind of format it's in, because raw images are just the pixel data with no metadata. So no real practical format would use raw image formats. Okay, there's a bit of confusion here. See, when I try to open this guy in PhotoViewer thinks it knows how to open raw images, but that makes no sense. There are a lot of digital cameras have what's called a raw format, but their raw format still has metadata in it. But there is something called the raw format in most modern cameras, and it's what it is. I think it's just, it has metadata, but it doesn't do compression. Okay, so I think what most cameras now call raw format are formats that don't do compression, but do have metadata. So they're more like this PPM file. Okay, they're more like that. BPM is another example of a format that's not compressed, but does have metadata. But the metadata in PPM files is itself binary. It's not ASCII metadata. PPM files have binary metadata followed by binary pixel data. BPM stands for bitmapped files. So bitmap file is an uncompressed file format where the metadata is up here. The metadata is somewhere stored in this stuff here, but the metadata is itself also binary. This file format's real nice because the metadata is readable in a text editor, so you can open the file up and see the metadata, and then the pixel data is below. This file format's weird. Nobody really uses this. Is an ancient file format. The metadata is in ASCII, and the pixel data is in ASCII also. Okay, so PhotoViewer thinks it wants to read raw data because you might actually send me a raw picture out of your camera. So there are people, photographers sometimes send each other raw pictures. They'll be huge files. It'll be the uncompressed data straight out of their camera, but it will have metadata. But when raw, they usually just mean uncompressed. Okay. All right. So that's a little bit of stuff about image files. Okay. Now let's go and look at the code. Okay. Here's an example program to just, here's what it looks like to just create a frame buffer. See, I create a frame buffer with a width and a height, and then I'm just going to fill that frame buffer with RGB, RGB, RGB values, and then I can tell the frame buffer to write itself to a file name. Okay, so if I compile, I can compile this, run it, and that file created this PBM file. Now, what that program did, if you look at it real carefully, it really just wrote rows of R and G and B. So for example, if I magnify this, whoops, you can kind of see it. It's just vertical strips of G. It's just vertical strips of RGB. So it doesn't look very nice, but it's actually holding vertical strips of RGB. Okay, so create a frame buffer, set pixels in the frame buffer. There's the row, there's the column, there's the color to put at that pixel. After you've done nested for loops will do a two-dimensional array. So you go across the rows, go across the columns. For each row, usually we process files row at a time. That's kind of just traditional. You don't have to do it row at a time. You could do it column at a time. So this is doing for each row from row 0 to whatever the height is. Then this one moves across a row from left to right, and this puts a pixel in it. Then you can dump it. Okay, so that's the bare bones of working with frame buffers. Create a frame buffer. Nested for loop will step through the whole frame buffer, then you can dump it. Okay. Here's another example. Oh, this example creates the same image file without using the frame buffer interface. This one, see, uses the frame buffer class to make things easier. This one would be what you would do if you were working with the file in a raw yourself. So this is going to create a raw file where it just opens the file, but it creates its own pixel buffer, fills the pixel buffer, then writes the pixel buffer to a file. Does not use the frame buffer interface, but that just means you have to write more code. So these two files create the same picture, but this one uses the frame buffer interface, so it's less code. If you use the frame buffer interface, it's better than doing everything yourself. Okay. This one does a little bit more work with a frame buffer. Let me run it and show you what it. So compile and run this one. It created this image. What it did is it created a frame buffer, filled it with vertical stripes, created a viewport and filled it with random pixels, and created another viewport and copied the Yoda picture into it. Okay, so it created the frame buffer. Then this is the part that puts the stripes in the frame buffer. So it fills the whole frame buffer. This fills the whole frame buffer from first row to last row, from first column to last column with the RGB stripes. Okay. Then it creates a viewport in the frame buffer. Creates a viewport. So the viewport starts at upper left-hand corner. See, it says 64, 64. If I go over here and I click on that upper left-hand corner, I can see that I'm at 65. Yeah, if I try a couple times, I can probably land right on 64, 64. But you can see that the upper left-hand corner is 64, 64. And it's 256 bytes wide by 128 bytes tall. So it's 256 columns and 128 rows. And then it's just filled with random data. So this is like a noise image. So there's a noise image in there. Okay. Notice that I just set pixels in the viewport. Notice that I'm using viewport coordinates here. I'm starting at row 0. Row 0 now in the viewport is the top row. Row 128 in the viewport is the bottom row. I don't have to worry about where I am in the frame buffer. I can use viewport coordinates while I'm working in the viewport. That's the beauty of viewports, is the viewports give you a local coordinate system, so it's much easier to work in that local coordinate system and let the frame buffer take your viewport coordinates and turn them into frame buffer coordinates. Like that pixel right there in, see, Earthframe View gives me the frame buffer coordinates. So that pixel right there is at 163, 118. But that's not its viewport coordinates. Earthframe View doesn't know anything about the viewport. It sees the viewport, but it doesn't know that there was a viewport there. So Earthframe View can't give me viewport coordinates. Okay. I could get viewport coordinates out of Earthframe View. I can do the following. I can highlight that little region there, edit, crop it, and now if I really wanted to, I could click on this and get viewport coordinates. See now, because now I've made it its own frame buffer in Earthframe View. I've made this its own little frame buffer in Earthframe View. So now if I needed to, I can actually get viewport coordinates within that image. Okay, so Earthframe View is kind of, pardon me?
What are the 64s for in the being passed? Yeah.
This upper left-hand corner, where the viewport starts in the frame buffer.
Got it. And then the size of it is 256,
Yeah,
128.
so it's upper left-hand corner with height. I could have made it upper left-hand corner, lower right-hand corner, and at one time I had it that way. The Java library, when it does this stuff, alternates between, like, you want to describe a rectangle. There's roughly 2 ways to describe a rectangle: upper left-hand corner, lower right-hand corner, or upper left-hand corner, width and height. The Java library half the time uses one way and half the time uses the other way. I decided that the better way is upper left-hand corner, width and height. That works better than upper left-hand corner, lower right-hand corner. Though sometimes even in my library, I use the upper left-hand corner, lower right-hand corner technique. Most libraries, it seems like nobody really 100% agrees on what's the best way to describe a viewport. Should you say nobody uses lower left-hand corner, upper right-hand corner. It would work, but for some reason, no one does lower left-hand corner, upper right-hand corner. You'll either see upper left-hand corner, lower right-hand corner, or upper left-hand corner with height. Okay, so upper left-hand corner with height. Okay, then you have viewport coordinates. Now, down here, I did 2 different things. How do you get Yoda in here? Well, you could do it the hard way or you could do it the easy way. The hard way is to open the Yoda file and copy pixels from the Yoda file into the frame buffer. Okay, so that's doing it the hard way, but you really shouldn't do it the hard way. If you want the Yoda picture to show up in here, you should actually, look, there's just one. Okay, here's the easy way to do it. 1 line of code. The easy way is to do 1 line of code. Tell the frame buffer to create a viewport at that location using Yoda as the data for the viewport. And in 1 line of code, you can have the library do the work for you. Again, always, if the library will work for you, let the library do your work. The less code you write, the better. Okay, so here is the, essentially doing it all the work myself. This is the work the library does for us. It opens the file, copies the pixel data from the file into the frame buffer. But all that's written into the frame buffer library. So you can just instantiate a frame buffer viewport. You can instantiate a viewport in the frame buffer at that location using that pixel data. Notice that if I give it this thing, I don't say what it makes the viewport, the width and height of the viewport will match the width and height of the Yoda picture. So you say what the upper left-hand corner is, then you say what file to use. And then that'll put that here. So I can recompile this now. The first time I ran it, I was doing it the long way. Then I can recompile it. And this time it ran and gave me the same picture, but I had the frame buffer do the work of copying that image into that viewport. Okay. Okay. Now here's another example. Oh, this one just fills the whole frame buffer with random pixels. Now there's a reason why that's kind of interesting. You know, here's the frame buffer. I'm sorry, 4. Random noise. Now there it's a JPEG file, and there it's a okay. There's 3 different file formats. Same pixel data as a PPM file, a PNG, and a JPEG. Now here's something real interesting. That's not compressed, right? That's compressed. What happened?
Oh, it didn't compress very much.
It actually did the opposite. What did it do? Here's the raw data. Here's the compressed version. What happened?
2 more kilobytes.
Got bigger.
Oh, it's got the metadata?
There's the metadata, sure. No, but this one has metadata also. This one does have
Oh,
metadata.
yeah, it's not raw. Okay.
Now, this one compressed it, but not a whole lot. It got a little bit of compression. Does anybody know why when you compress something it would get bigger? This is an algorithms question. If you ever go read the compression chapter in the algorithms book, does anybody, what's the point of compression?
Oh, this thing is all random, so you have nothing to compress really.
Right, there's no redundancy. It's purely random. There's no redundancy in there. So there's nothing to compress. And what's interesting is that the compression algorithm in PNG files doesn't work. JPEG still somehow manages to do some compression. And I think that's because JPEG does a lossy compression algorithm. So even though there's no redundancy in there, it still manages to compress it a little bit. If you go down here, notice that JPEG manages to do a lot more compression than GIF or PNG. JPEGs do really aggressive compression. They actually do it by changing your picture. They are a lossy compression. When you compress a picture with JPEG and then you uncompress it, you don't get back the same picture you started with. It loses information. So for example, I will bet if you zoomed in on this random picture, it does not look like this one. Because I bet that in order to compress it, they probably manipulated some of the pixels and they probably don't look the same. Now you wouldn't tell it from here, you'd have to zoom in, but I'll bet anything that if you zoom in on this one, it does no longer look like this one, whereas this one would. This one and this one will probably still look exactly alike. This one will probably look a little different because it's a lossy compression algorithm. You can't, in general, you can't compress random data. That's one of the key ideas in the theory of compression, is you can't compress random data. But if you're willing to throw some of the data away, like JPEG is, then yeah, you can even compress random data. Okay, so that's kind of an interesting experiment, that to create a random picture, then compress it with different compression algorithms and see what happens. Oh, here's another thing you can do. Take this file here and zip it. What happened when I zipped this file here? What did the compression algorithm do?
Got bigger.
It made it what?
1 kilobyte larger.
It made it bigger. Why? Yeah, that's because the compression algorithm puts its own metadata in there. And so it was not able to compress the picture, but it had to throw its metadata into there, and it ended up becoming even bigger. So zip couldn't compress this thing because it's random data. let's try another compression algorithm. Instead of using zip, let's use 7-zip. 7-zip was able to compress it a tiny bit. No, I'm sorry. No, 7-zip didn't compress it either. Didn't get bigger, but it didn't get compressed. So 7-zip, because 7-zip can't compress random data, okay? So 7-zip didn't compress it. Zip actually made it get a little bit bigger. The only one that could compress it was JPEG, and that's because JPEG's willing to throw away information. It's what we call a lossy compression algorithm. If you Google lossy compression, you'll see that those are compression algorithms where when you decompress, you don't get back what you started with. You get something that's good enough, but it's not going to be exactly what you started with. Zip and 7-zip are not lossy. They're what we call lossless compression. Okay, so because when you compress a text file, you certainly would hate to decompress it and get an approximation of your text file. But for image files, your visual system is pretty, it usually doesn't care about the compression algorithm in the JPEG class. The compression algorithm in JPEG is actually tuned to your brain. The information it throws away is information your brain doesn't notice. It's actually, they worked with psychologists. It's actually a real interesting story. They worked with psychologists and did a bunch of experiments, and they figured out what information in a pixel data the human brain doesn't see, and they threw out that information. And they kept what they think is the information that you really notice, which is kind of interesting that they could figure that out. So the compression algorithm in JPEG file is tuned to the human visual system. All right, let's look at another example. Here's a program that's kind of interesting. Let me close these. Let me compile this program. Now, if you run this program, it wants a command line argument. It wants to be told what file to work on. So I'm going to give it a file to open. I want to open this file here. So I'm going to tell it to open that file there. Oh, what did I do wrong? Oh, let me put it in. Oh, because it's got a space in it. See, the file name has a space in it, so I need to quote it on the command line. That's one of those little things. Windows is not very good about spaces in file names. So in Windows, you need to quote file names when they have spaces in them. Okay, now what did this program do? Here's the image, here's the original file. And what I produced was this thing. I found the edges. I wrote a program that finds edges in a file. It goes through a file and finds what look to it like the boundaries between things. It's called an edge detection algorithm. Okay, let's get another one. No, that's not a very good one. Oh, let's do Yoda. Okay, let's find the edges on Yoda. Okay, here's the Yoda picture, and here's his edges. Now, how do you write a program? Now, this is part of machine vision. You know, this is how robots reach for things. They have cameras, and their cameras run edge detection algorithms, and they find the edges so they can grab things. Okay, so this is, if you can Google. There's all kinds of edge detection algorithms out there. So I wrote a program that does a really trivial edge detection algorithm. Okay, so here's what it does. You tell it what file to open, and it opens it in a frame buffer. See, so it's taking the file that was on the command line. This is like your homework assignment. Whatever file's on the command line, it opens it in one frame buffer. Then it creates a second frame buffer that's the same size as this frame buffer. That's where the output's going to be. So the second frame buffer has the width and height of the original frame buffer. Now, notice that when you create this frame buffer, the frame buffer will read that file and give itself the dimensions of that file. So now this frame buffer knows how big that file is. So when I create the second frame buffer, I can ask the first frame buffer how wide you are and how tall you are. Okay, and I filled the frame buffer with black to begin with. So I give it a black background. Okay, now I want to go through the original frame buffer, which holds Yoda. And what I'm going to do is I'm going to do a derivative. Here's where the idea is. Look at an edge. Where you get an edge is when a color changes a lot. When you move one pixel, you get a big change in color. Now, look at Yoda's face. When there are edges in his face, notice that this guy didn't find them, because we see the edges, but there's not a big change in color from one part of his face to another. But there's a huge change in color when you cross the boundary of his body. Or look, the part of his clothing. See, there's big changes in color. Now, a big change is a delta. So here's what this program does. It walks the whole pixel. So for every row and every column, it picks so you pick a pixel. So this picks one pixel. You get the color at that pixel. So you're at that X coordinate, Y coordinate. Then you get the color above him. See, one pixel. Well, did I maybe?
Well, you might have labeled those wrong.
Oh, yeah, I think I labeled them wrong. Yeah, Y minus 1 is one pixel above him. This is one pixel below him, because the Y coordinates go down and the X coordinates go across. So yeah, I have these mislabeled. Okay, but notice I want the 4 pixels around him. I pick a pixel and I pick the 4 pixels, one to the left, one to the right, one above, one below. Then I create deltas. How much change is there between the pixel and the pixel on his right? And I do that for the RGB color. And then I take the delta H. Delta means change in. H is horizontal. I just take the maximum of the RGB deltas. Then I do that for vertical pixels. I ask how much change in color is there in the red? How much vertical change in red is there? How much vertical change in green is there? How much vertical change in blue is there? Okay. And then I take the maximum of that. Now that gives me a delta X and a delta X horizontally and a delta Y vertically. Then I can calc 3, I compute the gradient vector. The gradient vector is just the length of the vector that goes delta H in the X direction and delta Y. So this is delta X squared plus delta Y squared square root of it. So this is the Pythagorean theorem. I'm creating the gradient vector. And then I ask, is the gradient vector above a certain threshold? Is there a big change? If there's a big change, I color it white because I'm on an edge. And if there's not a big change, I just leave it black. Okay, that's a simple edge detection. It's computing the gradient vector of this picture. It's treating the picture as a function and computing its gradient vector. And it turns out that's the heart of machine vision. That turns out to be the heart of most machine vision algorithms that do edge detections. Okay, notice how simple this. Notice that this is just not even one page of code. Okay, and then notice I'm reading in the original frame buffer, and I'm writing to the second frame buffer. So I'm reading this picture and I'm writing this picture, and I have a baby algorithm for finding edges in pictures. Okay, so this is the kind of thing you can do once you have a nice frame buffer class. Notice that I don't need a frame buffer class to do this. I could open this file and just manipulate it directly. I could save this data directly, but the frame buffer makes it real easy. You can read pixels and set pixels much easier. So the frame buffer makes it nice to do manipulations. Okay, so And then I do a little bit of work on the name. See, I take the name of the file that I'm reading in, and I append to it the word edges, and then save it as a PPM file. So whatever file was read in, it's saved as its edge detection version. So whatever file is read in, it's saved as its edge detection version. Okay, so you can do a lot with this. Is now what we call image processing. It's not computer. If you just work with a frame buffer, you're really doing what we call image processing, not computer graphics. So most of this is in the field of image processing, which is a big part of modern AI. Nowadays, people want to do image processing with artificial intelligence. Okay, so but this gives you a sense of how you manipulate pixels to do things with pictures. Okay, we ran out of time. We've run out at the end of the course. Anybody got a last minute question? Anybody got a question they want to ask?
No, sir. Yeah, I'll put the video up for this on the website. Your homework assignments due a week from today, right? Yeah, homework assignments due a week from today. I can't think of anything else. We're going to start talking about 3D graphics on Thursday. We're going to start talking about the input data structure to our render instead of the output data structure. I think we know as much about pixels as we need to know at this point. And your homework assignment really makes you work with the frame buffer class. So that's as much as we need to know about pixels. And then the rest of the class is going to be, the frame buffer data structure never changes the whole rest of the course. But it's the input data structure is where all the work is going to be. We want to be able to describe 3D graphics in more and more elaborate ways. So we'll be working for the whole rest of the semester with the input data structure. Okay, if there's no question, I'm going to go ahead and stop sharing. And I'm going to end the meeting, and in a little while, I'll have the video up. And if you have any questions, just send me an email. Okay, so I'm going to end the meeting for all. See you on Thursday. Goodbye.